Then our first talk of the afternoon session is Pevtsova from the University of Washington, speaking on support theories for the stable module category of a finite group scheme.
Yes? No?
Not really.
Is it better? Oh yeah. Now I can hear myself. How about now? Good? Okay. Right, so if you couldn't hear me, you know? Is it better? Good? Okay, just let me know if you stop hearing. Thank you very much for the invitation. It's great to be here. And great to be in such fantastic company of speakers. And the first lecture is going to be sort of the introduction to finite group schemes and their representation theory. Right, and the pictures. So there are some pretty pictures, and I hope I'll get to them at some point. But if I don't get to them during the lecture, maybe you can look at them during the break. So, first of all, the setup. I'm going to work with a field of positive characteristics. Almost always. And I'll probably assume it's algebraically closed for convenience. And my main object of study is going to be a finite group scheme. Let's start with affine group schemes. An affine group scheme is simply a representable functor called G from commutative K algebras to groups. I'm going to take this functor of points approach to schemes. Now, the fact that it's a representable functor means that it is represented in algebra, which we are going to call K of G. This is the coordinate algebra. And our group scheme is a functor simply given by homing out of the representing object. I should probably give you a warning. Try not to erase that. I'll try to write this fancy K for as long as I can, but at some point it will probably morph into something like this. And all various other versions of K, it's going to be usually the same field K, or ground field K. Okay. So that's an affine group scheme. All my group schemes are always going to be affine. Now, just this way, it's set, so it's a scheme. The fact that it's a group scheme amounts to the algebra having the structure of the Hopf function. So the product here gives us the co-product in the representing algebra, and this gives an anti-equivalence of categories. So we have one-to-one correspondence between group schemes, and my group schemes are always affine and algebraic. And finitely generated commutative Hopf K objects. So G goes to its coordinate algebra, and the coordinate algebra goes to this representable functor, which gives a group scheme. See if I can work the technology. No? Okay. Okay. And do I have to stop it, and does it just stop automatically? Let's give a couple of examples, which sure almost everyone has seen, of group schemes. The easiest one is probably the additive group, called GA. So to give an example of a group scheme, I have to tell you what it does as a functor. So I have to take algebra, R is going to be K algebra, commutative K algebra, and evaluate my group scheme on this algebra. And this is going to be simply the additive group of the ring R. It's not hard, it's actually a nice exercise, to write down the coordinate algebra. And this is simply a polynomial ring on one variable, K of t. And we want to have a group scheme. This must be Hopf algebra. So we give the structure of the Hopf algebra, the coproduct. And it is simply given by making t into a primitive element. Then there is also the augmentation map, or the co-unit map, and the antipode in the Hopf algebra, and this one sends t to minus t. So this is the co-algebra structure, my coordinate algebra, and it translates into the group algebra structure here, which is simply that. Maybe, yeah. Another example is the multiplicative group. Again, I just have to tell you what happens for algebra, and here I take a multiplicative group. So a group of invertible element, my algebra. Here the coordinate algebra will be a ring of Laurent polynomials on T. And the Hopf algebra structure, some T to group-like element. The antipode sends T to T inverse. Maybe the most important example, sort of the example that covers everything else, in a sense, is the one of GLF. So you can think of the matrix of the general linear group as a group scheme. And what does it do? Well, we just take invertible matrices. This enters in R. So n by n matrices, and they must be multiple. And multiplication is matrix multiplication, the group scheme. The coordinate algebra here, which we'll come back to a few times, is just polynomial algebra on basically the matrix variables and square of them. But we also localize at the determinant, or we invert the determinant. And the Hopf algebra structure, very similar to matrix multiplication. So xij goes to xil tensor xlj. The co-unit, the augmentation map, sends xij to delta ij, and the inverse, well, if you haven't seen this, this exercise to do. Just have to know how to invert matrices. study finite group schemes. Here's the definition. Affine group scheme G is a finite group scheme which I'll abbreviate as FGS, not to be confused with FSG, which is a finite simple group, even though finite simple groups are examples of such. If simply the coordinate algebra is finite dimensional as a vector space over K. Now in this case, the following thing happens. So this is a Hopf algebra, and it's finite dimensional. We can take a linear dual of this Hopf algebra. I'm going to use Marcos's notation for the dual. And I'll call this the group algebra of G. And now this one is finite dimensional once again. Now the coordinate algebra is commutative, so once we dualize, we get the co-commutative algebra, co-commutative Hopf A algebra. And again, going through the coordinate algebra, we get an equivalence of categories between finite group schemes defined over my code, okay? And these things, finite dimensional, co-commutative of K algebras. I'm going to be interested in representations and cosmology of these structures, and one key aspect of them is that one can look at them both algebraically, just work with this co-commutative Hopf algebras, or geometrically, since they come from group schemes and they actually have a lot of geometry. And that's the reason we are able to do various things with representations of this particular algebras, which we often cannot do for more general settings. It's this, the juxtaposition of the geometric and algebraic points of view. Metric, and this is algebraic. Particularly when you learn about the subject, usually there are at least two definitions for everything. The geometrically minded definition and the algebraically minded definition. And what interested in are representations of G, so representations of my finite group scheme, which we can define from the geometric perspective, the way we would define representations of algebraic group, but they're also going to be equivalent to algebraic interpretation of co-modules for the coordinate algebra, and from now on I'm going to assume that G is finite group scheme. This works for any affine group scheme. So this will be modules for the group algebra. I'm going to try to stick to the following convention. So in everything I do, I'll be interested in both finite dimensional modules and all modules, so particular infinite dimensional modules. And the convention is going to be, if there are capital letters, this refers to all modules. But if I only use small letters, this should be finite dimensional modules only. If it's ever unclear, please ask. For some of the statements, it's going to be important which modules we look at. Okay, so if we only look at finite dimensional representations, we have all the same equivalences. they're the same as KG modules. And once again, here we'll have a geometric point of view, and here have an algebraic point of view for the same object. And this really gives you a lot of tools to work with. I mentioned that this is an abelian category, but it is also a symmetric monoidal category. It has a tensor product. So we have, and we can view it from the algebraic perspective, two modules M and N, and tensor them over K, so it's an exact functor, and the structure of a KG module is given by the coproduct in this Hopf algebra. If you view them as representations of finite group scheme, then it's going to be diagonal action, just the way you do it for finite groups. Okay, examples. So the first example of a finite group scheme is a finite group. And unless you've thought about finite group schemes, you probably have not thought about finite group as a representable functor or as a scheme, but you can. So it fits into this context very nicely. I'm going to call my finite group pi. And there's one thing which is very tempting to do. You want to define a functor associated to pi. So just say, so let's call it pi var. So we just have to say what happens when you evaluate it on commutative algebra. And we can try to write pi, just give this finite group as your functor of points, but that's not going to quite work. We have to take several copies of pi depending on what our algebra is, otherwise it's not going to be factorial. So this is just the set of connected components of the algebra R. So in particular, if it's, say, local, then you just get pi, but otherwise you can get a bunch of copies of pi. This turns out to be factorial correspondence. And the group algebra of this functor will be the group algebra of my finite group. Right, and the reason, I'm using this for the group algebra, no brackets, because brackets would mean the dual for this, like ordinate algebra, which is going to be very different. But this is just the usual group algebra. The coproduct is just given by sending basis element G to G tensor G, the structure that you all know and love. And then representations of this as a finite group scheme are the same as just representations of the group algebra, the same as representations of pi as a group. So from a representation theoretic perspective, we get old, familiar, and mysterious representation theory of finite groups. Should probably say that these are called constant finite group schemes because they're basically constant as functors. They don't depend on the ring R very much. And if we sidestep from the characteristic P for a second and look field of characteristic 0 and assume it's algebraically closed, then any finite group scheme is going to be a constant finite group scheme. In other words, any finite group scheme is given by a finite group. So you don't get any interesting examples in characteristic 0. Even if we don't assume this, still, any finite group scheme is going to be what's called a tau. Oh, I think I had an abbreviation, so I don't have to write this out. So basically, it comes from a finite group plus some Galois action. So in characteristic 0, everything is described by finite groups. Now let's go back to characteristic P. I'm going to give an example which is very, very different. Restricted Lie algebras. So this already showed up, an example showed up in Marcus's talk, and just as Marcus didn't, I'm not going to give a definition of restricted Lie algebra, but I'll give examples instead. So we start with a Lie algebra, G, and it's restricted if it has extra operation, we call it P's power, from G to G, which is nicely compatible with the bracket. One can write down definition in axiomatic terms. There are several conditions they need to satisfy. This separation needs to satisfy to define a restricted Lie algebra, and this is called either a P's power or a P restriction map. This gives a lot of extra structure, but the Lie algebra only happens in characteristic P, and here is the main example. Let's say our Lie algebra is GLN. So just all n by n matrices, say over a field K. Then it is restricted, and the P's power is the P's power. Just take a matrix to the P's power. And you can actually read off the general definition from here, and the general definition sort of gives you an axiomatic description of matrix multiplication. If you have any Lie algebra, you can always embed into GLN. If it's restricted, it's going to be embedded as a restricted Lie algebra, and then this P's power will just be descended from the one here. Another example, restricted map, comes from the definition of Lie algebra of, say, an algebraic group. So now, I think I want to keep G for my finite group scheme. So let's say the curly G is an algebraic group, say GLN. And think of your favorite matrix group. Like if you're really numbered by E8, that's okay. And it has a Lie algebra, just as a Lie group has a Lie algebra. And it's a Lie algebra of left invariant derivations on the coordinate algebra. In fact, you can define it for any group scheme. So you look at left invariant derivations on this algebra. And the reason it's a Lie algebra is that if you write down the bracket of two left invariant derivations, you get a left invariant derivation. Now if you're in characteristic P, and you have a left invariant derivation, and you try to iterate it P times, then you use the Newton-Leibniz formula for that. And again, because in characteristic P, various nice things happen, namely all coefficients vanish once you get to the P's power. And it turns out that your P's power, P's iteration, is again a derivation. And that gives you this P restriction map for any Lie algebra of any group scheme. We have tons of examples. Anything natural you take, any matrix Lie algebra, anything that comes as a Lie algebra is going to be P restricted Lie algebra in characteristic P. That's a sort of huge source of examples, and this example of the restricted Lie algebras is very different from finite groups. And I'll try to point out how. But first, probably need to say how it is a finite group scheme. Any questions? So to show that something is a finite group scheme, I have a couple of options. I can either explicitly write it as a functor, or I can say that it is associated in a good way to a finite dimensional co-commutative Hopf algebra. So I'm going to do the second thing. Now if we have a p-restricted Lie algebra, then we associate to it called the universe restricted enveloping algebra. In the following way. So we take the universal enveloping algebra. This is something infinite dimensional that comes from the tensor algebra. And we factor out the following ideal. So we take x to the p, so x is an element in G. Now if you have an element in G, it's in here, you can multiply it by itself p times. This comes from tensor multiplication. But then we subtract this internal p's power. So this guy lives in G, whereas this lives somewhere far away from G. And it goes over all x in the Lie algebra, and the result is finite dimension. It also inherits the Hopf algebra structure, the usual Hopf algebra structure from the universal enveloping algebra. So it's a co-commutative Hopf algebra. Maybe you can point out that it's not just finite dimensional. We can write down what the dimension is. So this guy has a PBW basis. So let's say x1, yeah, I'm assuming my Lie algebras are finite dimensional. xn is the basis of G. Then we'll have the PBW basis, so all monomials. But now, if you're in this quotient, you take a monomial, and once any of the powers is up to p and higher, you can replace this thing with something in G. So for your basis, you only go up to p minus first power everywhere. You get an algebra of dimension p to the n. And just as for a regular Lie algebra, representations of that Lie algebra are the same as representations of the universal enveloping algebra, restricted representations of restricted Lie algebra, the ones which respect the p's power, are just representations of the restricted enveloping algebra. So for representations, we have an equivalence of categories between representations of G and representations of U of G. So from that sort of roundabout point of view, Lie algebra is a finite group scheme. Let's contrast the Hopf algebra structure here and for the group algebra of a finite group. If we have a finite group and we look at the group algebra, then maybe I shouldn't call element of group G x, y, the coproduct makes all elements from the group group-like. The whole thing is generated by group-like elements. Whereas we have a restricted Lie algebra, the corresponding Hopf algebra is restricted enveloping algebra, and then for any x in G, the coproduct comes from the coproduct in the universal enveloping algebra, and it makes x into a primitive element. So this algebra is primitively generated. So, as far as Hopf algebras go, these are on the opposite end of the spectrum. One has only group-like elements, the other has only primitive elements. And there's a whole thing of, you have a lot of stuff in between, but the Hopf algebra structures basically are orthogonal for these two things. That's one reason they are so different. Okay. Yes? Here? Oh, yes. Thank you. Already going against my own convention. Thank you. Now, the second example was sort of cheating a little bit, because I didn't really tell you how Lie algebra is a group scheme. I'll do it now. So this is a third example. Again, because we're in characteristic P, if we start with, let's write a curly thing, so any group scheme, but you can think of any of your favorite matrix groups, like GLN is always a good one to have in mind. We have a Frobenius map. Now for GLN, write it down explicitly, we have a matrix here, and we just take all entries to the p's power. Does it actually make sense? Am I right here? I'm being a little casual, because I'm thinking of GLN as a group scheme. So GLN itself is a functor. So I'm thinking about plugging in some algebra, and then taking a matrix with coefficients in that algebra and doing this. So I'm just going to skip the algebra. But it's just taking pth powers of all the entries. In general, if your group scheme is not defined over the prime field Fp, then you have to take a little twist here. But basically, it's almost the same thing. As a variety, it's the same thing here. And then you have an honest Frobenius map. You can define it algebraically, in a very explicit way. And you can take the kernel of this map. In fact, you can take any kernels of this map. You can iterate it, say, r times. And the kernel, scheme group theoretic kernel, is called the Frobenius kernel of G. And this is a finite group scheme. And again, it's a very rich source of examples of finite group schemes. We quickly write down what we get if we do this for the examples that we've seen. So for GA, which is defined over P, so that you think of my Frobenius map just going from GA to J. It just simply takes R to R to the P. Once again, I'm thinking of evaluating GA in some algebra R, so this R is an element from that algebra. I'm taking it to the p's power. This is a map of groups. The reason this is a map of groups is, I don't know, we call it the freshman calculus rule. Right? If you have R and say R prime, to the P, and you can use this rule. And somehow all of them do. Anyway, no, I always tell them that just work in characteristic P, and after that I usually don't get any questions at all. Okay, so it's a map of group schemes, and we can write down the corresponding map of group algebras, on the coordinate algebras. It simply takes T to T to the P. And then the kernel, well, okay, as a group scheme, evaluated with some R, is simply all elements in R which go to 0. So all p-nilpotent elements in R. Again, it's a group scheme. It's finite. The coordinate algebra of this first Frobenius Colonel of GA is k of t mod t to the p. Right? We just want all elements with the p's power 0, so they picked out by taking maps from this truncated polynomial algebra. This often shows up in a different name, like I've seen, which is alpha p. This little tiny finite group scheme, and it has this property, it doesn't really have points. When I was still a graduate student, I was once given a talk at a topology seminar, and it was all about infinitesimal group schemes. I'll say what they are. But basically, they have this property that if you try to evaluate this functor on a field, you're not going to get a lot of points. Right? If you plug in a field here and you look at all elements, new field with p's power 0, you don't get very much. So from point of view of classical algebraic geometry, if you only look at your variety and you look at points over a field, you don't get any points. So the question I got was, so why don't you study these completely pointless objects? So, okay, they are, but at the same time, as I hope we agreed, representations of this object are the same as representations of this thing. We have characteristic P, so this is actually just the group algebra of a cyclic group. And representations of cyclic group are, you probably can agree, rather interesting. Certainly not pointless. So infinitesimal means that the coordinate algebra is local. And it does mean that if you plug in a field, you don't get very much. These things are also called infinitesimal neighborhoods of the identity in G. So the Frobenius kernels are infinitesimal neighborhoods of the identity of my group scheme. I can quickly write down a couple more examples. For GM, let's say what happens. If you take a Frobenius kernel, you get is the group of roots of unity. And it's the same thing, the Frobenius map is going to be taking r to the p's power, but now the structure is multiplicative. So to take the kernel, we have to see what goes to 1. But the coordinate algebra will be a quotient of the Laurent polynomials by the same thing, t to the p minus 1. And again, using the freshman calculus rule, we can rewrite this as k, say, of u mod u to the p, where u is t minus 1. So as an algebra, it is actually isomorphic to the coordinate algebra of my previous example. But as co-algebras, they're quite different. And this one does have points, so completely pointless. And then again, the example that sort of encompasses all of them is going to be the R's Frobenius kernel of GLN R, of GLN. And the points here, for any algebra, are going to be matrices. And we have to make sure that the R's Frobenius map vanishes. The Frobenius map just takes each entry to the p's power. We do it r times. And we have to get to the identity matrix. So the condition is that we get 1 on the diagonal and 0 everywhere else. So this is the matrices we want to get. Once again, it's easy to see that if you plug in a field, you don't get very much. You only get 1 point. But again, this is a group scheme with very rich representation theory. And the coordinate algebra So this is going to be just polynomial algebra on n square variables, and we factor out the relations that come from this condition, x, I, g, j, p to the r minus delta I, j. And now that we don't have to invert the determinant anymore because the condition determinant comes from this relation. It's a huge algebra, and the representations are going to be representations of the dual. It's going to be very complicated, very non-commutative, but very interesting Hopf algebra. So these are the kind of gadgets on the study. And one tool we're going to employ is the Cosmology. Oh, right, I still didn't tell you what does it have to do with Lie algebras. Today, 14. So if you have, let's say, an algebraic group, or a group scheme, then you can take the first Frobenius kernel. This is going to be a finite group scheme associated to this guy. You can also take the Lie algebra. And then what happens is that, well, let's call it G. If you take the restricted enveloping algebra of this Lie algebra, or if we take the coordinate algebra of this first Frobenius kernel, they're dual. So this is a commutative Hopf algebra, this is co-commutative Hopf algebra, but we have an isomorphism. The Lie algebras are in one-to-one correspondence with Frobenius kernels. So this is the way they actually arise honestly as group schemes. Now this Frobenius kernels actually know quite a bit about the original algebraic group. If you start with something like GLN, an algebraic group, and look at Frobenius kernels, they sort of capture in some way, say, representation theory for GLN. For example, any simple module shows up as a simple module for one of Frobenius kernels. You just have to take R to be big enough. So they remember quite a bit about representations of algebraic groups. Okay, now one of the tools we're going to use is Cosmology. Say that this category of representations of G, or KG modules, is abelian. It has enough injectives. Again, mind G from now on is a finite group scheme. Moreover, it's a Frobenius category. So injective modules are projective modules, which is going to be important. In view of Marcus's talk, I probably should make a remark that this algebra is Frobenius, but not necessarily symmetric. It's very often symmetric. Like if this is a finite group, you know it's symmetric. It's symmetric in various other cases, but sometimes it's not symmetric. And this leads to various interesting things you don't see when you work with finite groups. And you'll hear about this phenomenon in Shrikansayan talk next week, where various twists in both direct and indirect sense will come up, thanks to the fact that the algebra is not symmetric. Okay, now, since we have a really category, we have enough injectives, we can look at Cosmology. So I'm not going to look at Hochschild Cosmology, I'm just going to look at rational Cosmology, or whatever you want to call it. This is simply the X groups between a trivial module. And this is the same as looking at this X groups over the group algebra. Or the Cosmology group algebra with coefficients in K. So the same thing that happens for finite groups. And we also have X for any two modules. I'm going to look at X with coefficients, X from K to M, or cohomology with coefficients in M. Now, in this situation, we have this algebra. Well, I should probably say that this is graded commutative. Again, just as Hochschild cohomology is, I'm actually not sure who to attribute this to. I mean, I can attribute it to Kirsten-Haber. I can probably attribute it to Cartan-Eilenberg, because the proof for finite groups is the same as the proof here. The proof I like the most is the one that uses Ekman-Hilton argument, and it's basically 3 lines and doesn't use anything at all. But anyway, it's not hard to show that it is graded commutative, and it acts on X for any two modules. And Marcus basically said what happens. But one can also think about this action in terms of unit product. I can do it this way. So I, J, I plus J, G, and N. Let's say it in words. You have an extension here between M and N. You have an extension here between K and K. You tensor an extension here with, say, M, and then you concatenate, and you get an extension here. If these two modules are the same, then we can also think about this as the map that again showed up in Marcus's talk. So this is just tensoring with M. You take an extension and you tensor it. Canonical algebra map. So this way, in particular, cohomology of G with coefficients in M is a module of over my cohomology algebra. And a very important property of finite group schemes is that cohomology algebra satisfies the FG property. There's a theorem due to Friedlander and Suslin. So if G is a finite group scheme, and M is a finite dimensional G module, then first, cohomology is a finitely generated K algebra, and second, HGM is a finitely generated module over the cohomology algebra. History, as we already learned, for finite groups. Oh, yes, thank you. Yes. If G is a finite group, then this is due to Gollett, benign for P groups, and then Venkov and Evans independently. So Venkov had a beautiful topological proof where you just embed any finite group into a unitary group, and there you know what cohomology is. Evans had no less beautiful, completely algebraic group where he came up with what's called Evans norm map. And this is 61, both of them. You notice there's a huge gap between these two results. And the reason is not that people weren't interested in finite group schemes, but this method just didn't generalize. Nothing generalized at all. So this was proven using the techniques coming from strict polynomial functors. And I'll do test someone else. You'll hear about this in Antoine, not about this, but about strict polynomial functors, I presume, in Antoine Touzet's talk next week. Okay, so this is a theorem that sort of allows one to get started with geometric methods, together with another one, just due to Quillen. Okay, I think I lost my count. 17? So once it was known that cohomology is finitely generated, and cohomology is an important algebraic invariant. And the entire sort of industry of using geometric methods goes back to Quillen's totally brilliant papers in the Annals, 2 papers on equivariant group cohomology, where sort of he did start it all. So, Quillen. And he says in the introduction to those papers that he was thinking about a question, rather a conjecture, but I'll formulate it as a question, by Atiyah and Swan, for finite groups. So let G be a finite group. What is the Krull dimension? Of the cohomology algebra of G. So we know it's a finitely generated graded commutative algebra. If we actually drop the odd degrees, then we get an honest commutative algebra. What is the Krull dimension? Now, in Quillen's usual way, he didn't just answer the question. He completely described what this is geometrically. Now, to say what Quillen proved, I need a piece of notation. I actually need to tell you what is cohomology of an elementary abelian P group. So let's say E is an elementary abelian P group of rank M. Then the cohomology algebra we explicitly computed, and it's simply a polynomial algebra on n variables. These guys come in degree. Oh yeah, let's say P is not 2. You can do it in degree 2 as well, in characteristic 2 as well, just the answer is somewhat different. So they're in degree 2. Tensor exterior algebra in degree 1. Then the spectrum is cohomology algebra, and now I'm just talking about the prime ideal spectrum from the variety point of view. But for the spectrum, we can forget about the nilpotent elements and just look in the polynomial ring on n variables. It's just an affine space. And in fact, for what I'm going to do, I'll stick with the proj of this algebra since it's graded. Only look at homogeneous prime ideals minus the irrelevant ideal, and this is projective space e to the n minus 1. So I'll need that. Okay. And then Quillen tells us that we want to know what is the spectrum of cohomology of any finite group. And all we need to do is look at all elementary abelian P groups inside there. In those spectrums. Now, because cohomology is contravariant, we'll have this spectrum naturally mapping into this one, and you have E inside G, then cohomology inverts the map, and then we take spectrum that inverts the map once again. So if you have E inside G, then send the spectrum of cohomology of E to spectrum of cohomology of G. This is not necessarily an embedding, but it's a finite map. And then colimit, we take colimit for, we have to take into account inclusions of elementary BNP groups and conjugacy classes. So Quillen actually gives you a precise recipe how these guys are put together, and these are just affine spaces. But sort of the big form of Quillen stratification tells you that for each conjugacy class of elementary BNP group, you have an affine space, and then how do you put them together to get the spectrum in a very explicit way. So the geometric structure of this space depends only on the elementary BNP groups inside our group G. And of course, from this, one can read off various things about the spectrum. And the first thing which is immediate is the answer to the Krull dimension question. It's given completely independently of any cohomological properties. You just have to look at the maximal elementary BNP subgroup. Because the dimension of the space is the Krull dimension, and it's precisely the rank of E. So it's just the maximal rank in elementary BNP subgroup. And I lied a little bit. So TS1 actually conjectured that. So they knew what the answer should be, and Quillen knew what the answer should be. But he proved it in a very beautiful way. Now, when do you have to stop? 5 minutes? I was going to give you an example of how this works in the smallest possible case of D4. But actually the pictures, if you had any time to look at the pictures, I think once I'm done, I'll show them again, were illustrations of the Quillen stratification theorem. So they had much more difficult examples, and I'll maybe try to explain a little bit what they were. But basically, they were pictures of spectra of cohomology for various finite simple groups. Maybe before I get there, I can still don't have enough time to state what happens for Lie algebras. So Lie algebras are also finite group schemes. Cohomology is finitely generated, so one can ask whether there is anything along those lines, along Quillen's lines, then one can write for Lie algebra. Can we say what Krull dimension of cohomology is? Can we describe cohomology geometrically? Again, all my Lie algebras are restricted. And it turns out that yes, we can, and that the answer doesn't look anything like Quillen stratification theorem. So first I need a piece of notation. So if G is my Lie algebra, then a restricted null cone of G is a subset in G, which consists of all elements with piece power, restricted piece power 0. So in characteristic 0, in geometric representation theory, looking at the null cone is very important. You look at all nilpotent elements. Here, we look at P nilpotent elements, although if you're working with a reductive Lie algebra, the algebra of some algebraic group, semi-simple algebraic group, which is, and P is big enough, then it turns out to be the same thing as a null cone. And here's the theorem. Friedlander and Bendel, 97. And it says that the spectrum of cohomology of G, okay, I should say that Here I'm thinking of G as a finite group scheme. So this is just cohomology of the restricted enveloping algebra. It's not what you usually think of cohomology here when you just plug in the universal enveloping algebra, in which case, from the geometric point of view, you don't get anything interesting since it's just non-zero and finitely many degrees. So this one is infinite dimensional algebra, finite full dimension, and this is homeomorphic to the restricted model. One can compute the spectrum explicitly, but the answer doesn't look anything like the equivalence stratification theorem. So first of all, for any respectable finite group, that space is going to be reducible. If you have at least 2 conjugacy classes of elementary billion P groups, you'll get a reducible space. But still, it's a space which you put together of just affine planes, affine spaces. Maybe there are some finite maps involved. Here, you get null con. It's singular, always. It's, for reductive Lie algebra, it's always irreducible. There's very different geometric properties. But it's as close as you go to equivalence certification. I think, stop here. Maybe we can quickly look at pictures. Which one is the projector? Oh, okay. Okay. So is it thinking or do you have to do something? Okay, so let's see, I think this one is a, oh, right, let's look at that. So this is A14, it's the alternating group of 14 elements. This represents the structure of either the spectrum of cohomology or elementary abelian P2 subgroups, so characteristics 2, inside the alternating group. So what this tells you is that the maximal rank is 6. You just count the rows. So the top row is going to correspond to elementary abelian P group, 2 groups of rank 6. Then the edges gives you the inclusions. So if 2 things are connected by an edge, this means that the dot corresponding to something is the subgroup of the dot to which the edge goes, and it goes from top to bottom. And then the colors actually represent the conjugacy classes. Oh, sorry, no, I take it back. So the dots are already conjugacy classes. Right, the colors represent conjugacy classes under something else. Get to that. But so if you ignore the colors for now, this is the structure of elementary abelian subgroups, and this gives you the structure of the variety. So here, I think if you look at it carefully, you can see that for alternating group, you'll have 4 components of dimension 6, and this tells you how they put together, and 2 independent components, just 2, of dimension 5, which don't lie in any components of dimension 6. So in particular, it's not an equidimensional thing. And everything else you can read off from here. Maybe one more. Something. Okay. So this is GL4 on F5. The 4x4 matrices on a field of 5 elements. Again, so rank 4, so dimension is going to be 4. There's just 1 component of maximal dimension, tons of components of dimension 3. And here, the colors actually represent conjugacy classes under GL4, under the algebraic group. So you have algebraic group acting on this whole thing, and so it gives you a little bit more structure, and colors correspond to the conjugacy classes there. But anyway, that's the combinatorial structure of spectrum. If you want to know number of reducible components, dimension, whatever else, it's all there. And maybe you had a chance to look at pictures. see this one beforehand. So this is a symplectic group SP6 on SF2. And I should give credit, so these are not my pictures. They were done by a younger mathematical brother of mine, Jared Warner, in his thesis last year. And he can actually generate a lot of those. Okay, stop here. Thank you. No, this is a variety. So the way I think about it is, should have some done. So think of a null cone as a variety, so it's inside. Now this is just, you can think about it as an affine space. It's a linear variety. So this is the spectrum of the symmetric algebra on G dual. And this is a subvariety given by the equations that x to the p is 0. So it's a variety. And I think of this as a variety spectrum as well. And this map actually is, it's an isogeny, or what Quillen calls an F isomorphism. So it's much better than the homeomorphism, but it's not an isomorphism of schemes.
So are the pictures available somewhere on the web?
No. So I have to ask for permission. But maybe what I should do is ask for permission to post them somewhere. And I'll have to ask. But maybe the best thing to do would be for the thesis where pictures are to appear in a certain canonical place.
Also with some explanation.
Yes, yes. So thesis is good because it says what this whole thing, what this thing means, what the graph represents. Yeah, I'll try to sell this idea to James.
I think that there is a coffee break waiting for us upstairs, so let's thank Julia again.